In this video, we're going to talk about the Haber process with respect to Le Chatelier's principle. And so the Haber process is the reaction of nitrogen gas with hydrogen gas to make ammonia, which is an exothermic process. So I'm just going to add a couple things in here. Okay. So what we're going to do is we're going to make changes to the system and perturb that equilibrium, and then we're going to talk about what would happen in order to compensate for these changes. So we're going to take a look at things like adding or removing reactants or products, as well as changing temperature and pressure conditions. So first, since nitrogen and hydrogen are reactants, if we increase the concentration of those, temporarily we're going to have a higher ratio of products to reactants than we normally would at equilibrium, right? So K is our product concentration over our reactant concentration. And I'm just going to write it a little bit bigger for this reaction. Our K is going to be equal to ammonia, which is NH3, raised to the second power because it has a coefficient of 2, over N2 and H2 to the third because it has a coefficient of 3 in the balanced chemical equation. So anything we do that makes the numerator bigger than it should be at equilibrium is going to be compensated for by going backwards. And anything we do that makes the numerator smaller than it should be at equilibrium is going to push the reaction forwards. And we can say the same thing about the reactants as well. So let's take a look at some of these situations. So if I add hydrogen gas, that's adding a reactant. That would essentially increase the value of the denominator to be higher than what it should be at equilibrium and make it so that our Q value, or these ratios at any point in time, would be less than K. So what that means is if our stress that we add is increasing our concentration of hydrogen, it's going to shift the reaction to the right. So you're adding a reactant, so it's going to want to make more product to compensate for that. As it does that, it's going to decrease the concentration of nitrogen, it's going to increase the concentration of ammonia, and it's going to end up releasing heat because heat is essentially a product, okay? Going the other way, adding ammonia. So if our stress is that we're increasing the concentration of ammonia, now we have a higher ratio of product to reactant than we really would want at equilibrium, and it's going to go back to the left in order to compensate that. So if it's going back to the left, now we're going to have an increased concentration of both hydrogen and nitrogen, and it's also going to consume some of that heat energy as it goes this way. So your heat content would go down. Now we're going to take a look at what happens if we remove some components. So if we remove nitrogen, right, then we're going to have a denominator that would be smaller than we should be at equilibrium. So if we remove a reactant, it's going to want to make more of it. So it would favor going to the left, okay? And if our stress is that we reduce this, okay, since we're going to be forming more reactants, this concentration would go up of the other reactant, and then our product concentrations would go down. Similarly, with H2, now we're removing this reactant, so we're going to be still favoring going to the left. If you remove a reactant, it's going to favor shifting to the left. So our concentration of nitrogen would go up, and our ammonia and our energy would go down. Now in the next case, we're going to remove ammonia. So we're removing a product. That is our stress. As that goes down, right? Now it's going to shift the reaction to the right because we have less product than we should at equilibrium. So it's going to favor going to the right. So if that happens, we're going to reduce our concentration of reactants in order to make that ammonia, and it's going to release some heat energy in the process because, again, this is exothermic. So all of these things are changing concentrations of either products or reactants, and they actually don't have any impact on K. They have no impact on your equilibrium constant. It just you'll have to either make more product or less product in order to compensate for it. Now we're going to take a look at temperature. So if I increase the temperature, okay, that is our stress, is that the heat goes up. What we've essentially done is added a product without changing any of the concentrations of anything. So if you add a product, it's going to favor going to the left to compensate for that. So now what would happen is we would decrease our concentration of ammonia as we do that, and our reactant concentrations would increase. But this now means we have changed our value for K. All right, so now we would have an increased concentration of reactants, so this becomes shifted, and our K value would actually, sorry, there's no application here, but for this case, since we're going to increase our reactant concentration, our K value would go down for an exothermic reaction. If we decrease the temperature, it's going to have the opposite effect. If we decrease the temperature, now we're removing a product, it's going to favor the forward reaction, and our reactant concentrations would go down, our product concentration would go up, and we would now have an increase in our K value. All right, so changing the temperature is the only change we're going to make to an equilibrium system that's going to lead to a change in our value for K. Now, when we're looking at pressure, we really only need to take this into account when we're talking about gases. And it's going to favor, if we increase the pressure, we're smooshing it, okay? It's going to favor the side that has fewer moles of gas. Mole of any gas at the same set of conditions wants to take up the same amount of space, so increasing the pressure on it is going to like squish it and make it want to take up less space. So if we increase the pressure here, in this reaction we have 4 moles of gas on the left side, or our reactant side, and only 2 moles of gas on the product side. So it will, if we squish it, it will increase, it will shift it to the right. So that means it would increase the concentration. No! Still going. It would increase our concentration of ammonia, and it would decrease our concentration of our reactants. However, it would not change, and it would end up releasing energy, but it would not affect our equilibrium concentration. And this would it would be more complicated, but essentially you're changing the molarities in a way that leads to it changing our value for Q, and it would work its way back to K by doing this compensation. If we decrease the pressure, it will favor going to the left where there's more moles of gas, so then we would increase our concentrations of reactants and decrease our concentration of products, and again, not affect the equilibrium constant. So just a review of Le Chatelier's principal worksheet. Hope you enjoyed.